Hi everyone, I'm Rishabh Agarwal, and today I'm going to talk about our work on deep reinforcement learning at the edge of the statistical precipice. This work is accepted at NeurIPS 2021 as an oral presentation. For more details, refer to agarwal.github.io/reliable. TLDR, our findings in this work call for a change in how we evaluate performance on reinforcement learning and machine learning benchmarks, for which we present more reliable protocols, easily applicable with even a handful of runs to prevent unreliable results from stagnating the field. Let's go to the main talk. Research in deep reinforcement learning predominantly relies on evaluating performance on a diverse suite of tasks to assess progress. However, most published results on deep reinforcement learning benchmarks compare point estimates of aggregate performance, such as mean and median scores across tasks, ignoring the statistical uncertainty implied by the use of a finite number of training runs. For example, here we show the variability in published results on the Atari 100K benchmark. We find that there is a fairly large potential for drawing erroneous conclusions based on point estimates alone. Beginning with the arcade learning environment, the shift towards computationally demanding benchmarks has led to the practice of evaluating only a handful of runs per task, exacerbating the statistical uncertainty in point estimates. As we move towards more challenging reinforcement learning benchmarks, evaluating more than a handful of runs will become increasingly demanding due to the increased amount of compute and data needed to tackle such tasks. So, how do we reliably evaluate performance? We argue that just fixing random seeds is not a solution. Similarly, evaluating more than a few runs is typically infeasible for computationally demanding deep reinforcement learning benchmarks. Furthermore, we emphasize using statistical thinking but avoid statistical significance tests because of their dichotomous nature, that is, significant versus not significant, and wide misinterpretations. Any performance estimate based on a finite number of runs is a random variable and should be treated as such. In this work, we provide three tools for reliable evaluation aligned with the principle of reporting statistical uncertainty in results. Let's walk through these tools one by one. Instead of using point estimates, which ignore statistical uncertainty and hinder results reproducibility, we recommend reporting interval estimates using stratified bootstrap confidence intervals. With n runs per task on each of the m tasks, we have a total of n times m random samples. Statistical bootstrapping seems to work well in this scenario for providing reasonably accurate interval estimates via these confidence intervals, or CIs for short. Aggregate metrics such as mean and median performance across tasks conceal variability in performance across different runs as well as tasks. While tables with task mean scores can reveal such variability, such tables are overwhelming beyond a few tasks. Standard deviations are frequently omitted from such tables, and mean scores present an incomplete picture for multimodal and heavy-tailed distributions. Instead of tables with per task scores, we recommend performance profiles with stratified bootstrap confidence bands. Performance profiles are typically used for comparing solve times of different optimization methods and are robust to outlier runs and tasks. These profiles show tail distribution of scores on runs combined across all tasks. They allow for qualitative comparisons at a glance. For example, one curve above another in such profile corresponds to stochastic dominance. Furthermore, we can also read any score percentile from such profiles. For example, the place where the curves intersect y equal to 0.5 corresponds to the median score. However, performance profiles often intersect, and we still need aggregate metrics for quantitative comparisons. Existing metrics are deficient. Mean is prone to outliers, while median is unaffected by zero scores on nearly half of the tasks and is statistically inefficient. Instead, they recommend alternatives from robust statistics such as IQM and optimality gap. Interquartile mean, or IQM, corresponds to the mean score of the middle 50% of the runs combined across all tasks. Compared to mean, it is robust to outliers. Compared to median, it is a better indicator of overall performance and results in smaller CIs and requires fewer runs to claim improvements. On DM control, which is a widely used continuous control benchmark, there are huge overlaps in 95% confidence intervals of mean normalized scores for most algorithms. These findings suggest that a lot of the reported improvements on this benchmark would be spurious, resulting from the randomness in the experimental protocol. Another metric we propose is probability of improvement averaged across all tasks. This answers how likely the improvement over baseline is irrespective of its size. Applying this on Procgen, a common generalization benchmark, we find that some of the claimed improvements are only 50 to 70% likely. So, our conclusions from this work are that we should use interval estimates as opposed to point estimates for reliable benchmarking. For qualitative summarizations, we should refer to our performance profiles. We also urge authors to provide individual runs for better statistical comparisons. Also, when we have only access to a handful of runs, we should use better aggregate performance measures such as interquartile mean and probability of improvement. See the linked collab for a quick jumpstart. Thank you.